Now we're going to talk about some underlying assumptions of the linear regression. Well, one thing which is just common sense is that if you look at the data, if you have just one input and one output, so you can do a scatter plot of the data, okay? And if you do a scatter plot of the data, then the data should naturally be following a certain trend line, okay? So and this line just becomes our model, right? So if you don't have this linear pattern, then linear model is just another good choice. So you either have to choose a different model, or you have to find some transformations of your data set so that the XY relationship follow this linear pattern. But let's look at this requirement in a little bit more specific way. So one requirement is that for each value of x and y, values of y are normally distributed, meaning that, so let's say again you have your, so that's your input x, that's your output y, and you have your observations. Okay, so that's your data set, and you try to plot a line through this data set. So if you fix a value of x, okay, so let's so if you fix a value of x, let's you take this specific value of x here, okay, and then you take all the values of y associated. So there's going to be multiple y's associated with this value of x, right? So it's going to be these, and these. There are multiple y's. So those values of y's have to follow normal distribution. So if you plot a little histogram here of those y's that corresponds to this value of x, you should see this normal looking bell curve. Okay, so again, if you fix x and you look at all the y's associated with this x, then those values of y are normally distributed. Another property or another requirement for the linear model is that the means of y lie on the regression line. Okay, so meaning that if you have something like this, okay, so and you have a line like this, right? So these values here, mean of the y will not belong to line. So for this case, so it violates assumption number 2. So the means will not be on the line, okay? Which means in this case, linear model is not a good model, okay? And third assumption is that standard deviation of those normal distributions is equal, meaning that if you have case like this, so it's going to be line, and first assumption is correct. So the values of y normally distributed. Normally distributed means they are equally line on the left and on the right of this line. The assumption 2 will also be satisfied here because the means of the y will be on the regression line. However, assumption 3, that the standard deviation of those y's should be the same, it's not going to be the same. So here, standard deviation is small. So standard deviation means how much values of y deviate from the line, right? And here, standard deviation is large. So here, assumption 3 is violated. This data set violates assumption 3. Okay. And the last assumption is that the values of y are statistically independent. Now, this assumption is a little bit harder to visually check. So assumption 1, 2, and 3, you can basically plot the data and you can say whether 1, 2, and 3 are satisfied. Assumption 4 is a little bit harder to check. And actually, linear model will work relatively good even if assumption 4 is violated. It's just your values of beta 0 and beta 1 will be slightly off. They're not going to be correctly calculated by the LM function. But in actually a lot of the cases, that's acceptable from the practical point of view. However, the assumption number 1, 2, and 3 are more critical, and again, you can just visual check them by looking at the plot. But if you have multiple input x's, then you cannot really do these plots anymore, so you actually have to do some automated tests of those assumptions, which R can do for you. All right. So let's go back to our model, to the equation. So we're going to look at the simple linear regression. Y equals beta 0 plus beta 1x plus the error. And if we look at this error term, we assume that error follows normal distribution. Again, that's basically, so the fact that it's normal, right? That's assumption number 1. Assumption number 1 says that y's follow normal distribution. Another way to write it, we say y given x and beta 0 and beta 1. So if you know x, beta 0 and beta 1, then y will follow normal distribution centered at beta 0 plus beta 1x and standard deviation sigma. So here we say that y follows, for each given x, y follows the normal distribution, the mean of the follow distribution given by the point on the line. So this basically says that mean of y is on the line. So this is assumption number 2, right? Assumption number 2, okay? And then the assumption number 3 comes here. So you see the sigma squared, the variance of y, does not change with x. So for every value of x, we're going to have the same sigma squared, the same variance. So meaning that the variance does not depend on x. So for regardless where you are in the x space, your variances around the line, how far the points lie around the line is going to be the same everywhere. Okay. And as we mentioned earlier, beta 0 measures the effect of y when x equals to 0, and beta 1 measures the effect of y on x, meaning what happens to by how much y changes if x changes by 1 unit. All right, and for the future references, we're going to introduce this new notation xf, means x future, and this will denote a new or future value we wish to predict at. So we're going to build the model given some data set, and then we want to predict the value of y for some value xf, which we haven't seen before, the model hasn't seen before, so that's some new value, and we're going to do the prediction for that specific value. All right. So let's look at this concept of residual and the concept of the line in a little bit more abstract way. So what we're going to introduce a new notation, y hat. And y hat is going to be what we call a fitted value or predicted value. Fitted value is just the point or the value predicted by the line. So if we take this x here, and we want to predict the value of y for this corresponding x, then we're going to find the point on the line that corresponds to this x, okay? And that's going to be y hat. The hat tells us that it is the point on the line, and it's basically prediction that corresponds to this x. And so we did it graphically here, but the way you do it analytically, you just take your x and you plug this x into the equation, to the linear equation, and you get value y hat is just the value that sits on this line. That's our predicted value. We call it prediction or fitted value. So y hat is predicted, or another word for it is fitted value of y. Okay, so y hat is something that comes out of the model. All right, and the residuals of the model are nothing but just the distances from the actual y's to the predicted y's. So if you take this point here, okay, so this is going to be the y that corresponds to this point, And the predicted value by the model for this specific value of x is just the point from the line, which is this point. So we're going to call it y hat. And the distance between y and y hat is the same distance here and here, is called the residual. And we use letter E to denote it. So I, so residual of the observation I is just the difference between the actual value of y and value of y predicted by the model. And you remember we want those residuals to be as small as possible. So the way we quantify whether we have a good linear model or not is by looking at the values of those residuals. And sometimes it's more convenient to look at what is called standardized residuals instead of the residuals themselves. Standardized residuals are just residuals divided by the standard deviations associated with each of those residuals. So you basically remove the scale, right? So if y measured in dollar scale, then this one will be measured in dollar scale as well. So the standardized residuals is dimensionless quantity. All right. Just remove the dimensions, and then it will allow us to compare standardized residuals across models. Okay. And then another concept we should mention is a concept of an outlier. Outlier is just a point that is far away from the line, meaning that residual for this point is large. All right. So that's how we calculate residual standard error. So if we have a data set, so we have data set, and data set is just a sequence of pairs, x1, y1, x2, y2, so it's pairs of the points, x and yn, so we have n observations, okay, and for each observation we have an input variable and an output variable, and we build a model. So we build a model that relates y with x, okay, so it's line plus the residual plus the error, because the point's not going to be perfectly line on the line. And then we can calculate the error associated with this model. So we just going to look at the deviations. So y is the actual value, y hat is the predicted value for the observation y, and then we're going to average them out. But instead of averaging out the residuals, we average out the squares of the residuals. And the reason we take the squares is because residuals themselves might lead to the cancellations. So some residuals will be positive, some residuals will be negative. And it might happen that at the end, the average across all the residuals is 0, even though they are not 0. So to avoid this cancellation of negative and positive numbers, we take the square, and then we take the average across those deviations squared, and then we call it the residual standard error. Essentially, the residual standard error is the measure of the quality of the fit. So we want to find a line that makes this residual standard error to be as small as possible. So that's our criteria. For finding the line, or in other words, fitting the model. Is to make s squared as small as possible, right? So essentially that's how LM function works. LM function will try to find values of beta 0 and beta 1 so that this s squared value is as small as possible. And once we have the model, then so I'm going to give a specific example. We're going to relate sales to the price. So you have a price of the product and you try to predict the sales. So let me write it in the beta 0 plus beta 1 price and plus the error. And you remember when we talked about the prediction or estimating the confidence interval for the mean. So it's actually going to work the same for predicting the sales. You remember the sales. Another way to write it: sales follows normal distribution, and the mean of the sales, so expected value, is going to be point on this line, and there's going to be sigma squared variance around this line. So if you try to estimate the confidence interval for average sales for a given price, then what you will get is what is called confidence interval. Confidence interval for the sales. So which means, so the way we interpret confidence interval, somebody asks you, okay, if I set price to be equal to 5, then on average, what type of sales should I expect? And you say, okay, on average, that's going to be the interval that you're going to see. And another interval associated with this variable sales is what is called prediction interval. And again, we talked about prediction interval back when we talked about the normal distributions. It's just if the question is what my sales are going to be next month. So in other words, you don't want to quantify uncertainty about the average sales for a given value of X, but you want to see what are the likely interval for the sales to be in the next month, meaning for this specific instance. Then this interval is going to be wider, and this interval is called prediction interval. So a prediction interval tells you what sales to expect next month. So it's basically a random draw from the distribution rather than trying to quantify the mean. All right. And in R, you can do those intervals. You can calculate. You can ask R to calculate those intervals for you using this predict.lm function. Predict.lm will take the model as an input, and you will take the new values of X for which you want to generate the prediction, and then you will have to specify that you want to generate it as an interval, like the prediction interval or the confidence interval. And the way you basically define the new value of input is you have to specify it as a data frame. So predict.lm will take data frame for the new inputs. And so here we specify price 4, 5, 6. So we want to generate prediction for three different values of price 4, price 5, and price 6. And then we're going to generate prediction and the confidence interval. And that's how the output looks like. So for each value of the price, you get the prediction interval and the confidence interval. So for the value of 3, you get the sales is going to be 431, so that's the average number, and then you get the prediction interval, which is relatively tight interval around this number, and then you get the confidence interval, which is actually a smaller interval around this number. So confidence interval is also always going to be smaller because you remember confidence quantifies uncertainty about the average sales rather than average sales in a given month. And then you can do multiple predictions. So when you specify multiple values of the price, the R will output for each of the new values of X that you specified will give you the prediction, which is called fit. So that's our Y hat. So fit is nothing, just our Y hat. So that's the point on the line. And then for each of those new values, it will give you the prediction interval and confidence interval.